Okay, here we are looking at our first Agda file, and the goal for this video is that we should get used to the syntax of Agda so that we can write our own Agda in the future and not just read things on the screen. So the first thing I'm going to do is I'm going to load the file in Emacs by doing Ctrl+C, Ctrl+L, or alternatively, if you don't remember this, you can go to the Agda menu and then here you get a list of all the commands you can do, including load, the top one. Let's do that and we see that everything turns into color, which is nice. And if you haven't got Emacs set up, by the way, then you can go to this website, AgdaPad, which is Agda running in the browser, and you click new Agda session, then you just get an Emacs window running in your browser, which is okay for playing around. But if you want to do something a little bit more involved, then I would recommend that you get your own Emacs setup, or Atom, or VS Code, or whatever you prefer to use, because this is fun for now, but not ideal in the long run. So I'm going to use my Emacs, and okay, so let's see if we can understand what's going on here. So the first thing I want to show you was just the silly anonymous function. So this is something you could have written in Haskell as well. It's the function lambda ab goes to a. So we take two arguments a and b, and then we return the first one. And I'm calling this const for constant, because it's just going to be constantly the first argument, no matter what the second argument is. Right. So in Haskell, we could just have written it like this. We don't have to give a type signature, but in Agda we do have to give a type signature, because our types are more advanced, so they're not always possible to infer them. But this is considered best practice for Haskell anyway. Right? You should always give type signatures for top level definitions. So this doesn't really matter so much. So let's see how we give the type signature. So first we give the name of the thing we want to define. Here I'm calling it const. This name can be almost anything, by the way. It's not like in Haskell where it has to start with a lowercase letter. I can start with an uppercase letter if I want. Reload it, that's fine. I can't start with some digits. Yes, I can actually. And I can put in random symbols, and Agda is happy. The only thing you have to be careful of is that because we are very liberal with what we can put in identifiers, then we have to put spaces between many things. So I have to put a space here between the B and the arrow, for example, because B, otherwise I get an error like this, because B arrow is a perfectly valid identifier name. So we have to put a little bit more spaces in between things. But again, this is usually good for readability anyway, so not really a problem. So I'm going to revert this to the nicer name const. Okay, so we give the name of the thing we want to define. We use a single colon to say has type, not the double colon like in Haskell. Single colon looks nicer anyway, if you ask me. And then to the right of the colon, we give the type of the thing. So here we see that this is something which takes two arguments a and b, which has type set. So there's some things to unpack here. First one is that set is the type of types itself. So here we're saying that a and b are types, and since these things are written in curly braces, that means that these arguments are implicit. So Agda is inferring these arguments for us. We don't have to introduce them. So you see that we introduced the little a and the little b explicitly. That's the little a of type A and the little b of type B, but we haven't introduced these things explicitly. If we wanted to, we could put them here on the left hand side, and then I can refer to them if I want, but I don't have to introduce these things explicitly. Agda is happy to infer them for me, and then it's often nice to not have to do things if you don't have to. Just leave the boring things to the machine to do. Okay, so we'll introduce these implicit arguments a and b, and then we have a function type. So this is the thing that returns a function of this type. So given an a, we have to return a function of this type, and given a b, we have to return an a. Right. And we use this lambda to introduce this function type. And one other thing we can see is that we don't have to use this notation for the arrow. We could also use a fancy Unicode arrow, which looks like this. And the way you type this is you do a backslash, and then you see down here you get lots of different continuations that you can do, and then if you just write TO for 2, then you get an arrow. Or if you do a backslash and an ordinary arrow, you also get an arrow. And you can play around with these things. And you see down here that there's one more continuation. We're either done, or I can do an N as well, and then I get a different symbol. So some people like Unicode, some people hate Unicode, and personally I like it sometimes. I don't like it so much in other times. So I like my arrows to be ordinary arrows for some reason. Okay, so we've given the type of the function, and then on the next line we give it its value. So we say that this thing which I claimed had this type is given by this expression. So it's a lambda expression just like in Haskell, 2 arguments just like in Haskell, and an arrow just like in Haskell, and then here's the body of the function. And again, if you like Unicode, instead of just a backslash like this, you could also do backslash lambda, and you get a fancy Unicode lambda, which might look a bit nicer. But it means exactly the same, it's just different syntax. Okay, so that's how you give basic expressions. Compared to Haskell, you have to give the type of top-level things, and otherwise, and you have to use single colon instead of double colon for having a type. Oh, and another thing is that we often, as a convention, use capital letters for the first capitalized names for types, such as A and B, or list down here. But nothing is forcing us to do this. I could also rename this to be a lowercase b, and it would work just as well. But just as a convention, we like capitalized names for types and lowercase things for terms, because types are big things and terms are small, down-to-earth things. Okay, so that's how you define basic things. This is how you declare data types. Again, just like in Haskell, but the syntax is a little bit different. So we start with the keyword data. Keywords are orange, so we can see them. And then we give the name of the data type we're declaring. So here I'm calling it list. And then here comes a parameter of the data type to the left of the colon. So I'm saying that the type A is a parameter of my data type. So I want to define lists whose elements are type A. So I need A to be a parameter. And then after the colon comes the type of the data type itself. So often it's just set to say that it's a type. But sometimes it can be something more advanced. Okay, and then comes the keyword where, and after that comes a list of all the constructors of the data type, which for lists are exactly 2. It's the empty list or it's a non-empty list. So we give the name of the first constructor, which here I've written as these square brackets for the empty list, and then I have to give the type of the constructor. So here we are saying that the empty list is a list. And for the cons, I give it a name, which we'll get back to in a moment. And I say that this constructor has type A to list A to A. So this is the head of the new list, and this is the tail of the new list. And if we give this thing a head and a tail, then we get a new list. Okay, so let's look at this thing. So first of all, it's a bit funny because it's just symbols, right? There's no names. So there's in particular no need, like in Haskell, to always have constructors starting with a capital or a lowercase name. You can start with anything. And secondly, we have these underscores here. And the underscores goes in the places where you want to put your arguments. So for example, if you want to define addition, then one good way to name this would be to say underscore plus underscore, to say that the first argument goes here, the second argument goes here. So that means that you can write 5 plus 7 instead of writing plus of 5 and 7. But it doesn't stop with just 2 arguments, infix. You could also define, for example, if, then, else with 3 underscores, which means that the first argument goes here, the second argument goes here, and the third argument goes here. So then you could say if true, then 5, else 7. So you get these mix, fix, and infix operators built into the language in the sense that you can define them yourself. It's not a fixed number of things that are infix, but anything you want can be infix or mix, fix. This is sometimes very nice, but it's also sometimes very confusing if you don't use it correctly. So you need to think if it's appropriate or not. So here we have one constructor, and the head goes here and the tail goes here on the list, because the head is the first argument and the tail is the second argument. We see that this sequence of constructors we're given, they come after the where block, and then they've been indented at least one space. Right? It doesn't matter if it's one space or if it's 5 spaces, but it has to be the same number of spaces, otherwise you get this error. So we often use 2 spaces, because that's about enough. And we know that the sequence of constructors is over at this point, because here we have been out-entered again. Right? We're not 2 spaces in anymore. So that's how we define data types, just by giving a list of its constructors and their types. And you of course have to make sure that the constructors actually construct something in the thing you're defining. If you're trying to claim that the empty list is of type A, then you get an error that the target is wrong. Okay, and here's another example of how you define a function. And this is exactly like in Haskell, except that we have to give the type explicitly. And again, we have to introduce the little a. It's not introduced for us by Haskell. So we say that we have an implicit argument where a is a type, and then we take a list of a's and a list of a's, and we produce a list of a's. And this thing is defined by pattern matching. So we have to give, and in this case there's a pattern matching on the first argument. So we have to say what happens if the first thing is the empty list, and what happens if the first thing is a cons. And then we give a case for each one of these. And we do a recursive call here by just calling the function again on some other arguments, just like in Haskell. So this should be very familiar. But we'll see much more of this later.